I'm Carol Jones from the University of Western Ontario. Thanks for joining us on our very first Zoom talk about focused on active B stars, and this is a result of our working group on active B stars, the IAU group. We're delighted that Jonathan has agreed to come and give our first inaugural talk. So welcome, Jonathan. Thanks to Mark Suffix, my PhD student, who has been very helpful setting up the Zoom and the links and managing the participants that are joining us. So thanks, everyone. So I'll give a brief introduction to Jonathan and then turn it over to him. So Jonathan Labadie-Bartz received his PhD in physics from Leahy University in Pennsylvania, USA in December 2017. His PhD thesis advisor was Joshua Pepper, and the thesis work focused on variability of BE stars, especially through the use of archival data sets. Jonathan spent about a year as a postdoc at the University of Delaware with Professor Veronique Petit in her research group, working on BE stars and massive magnetic stars. He has been at the University of Sao Paulo as a postdoctoral researcher since November 2018, working with Professor Alex Carcioffi's group, studying BE stars and their disks. His main research goals involve using space photometry from the TESS mission to study large samples of BE stars and other types of massive stars systems with a focus on their variability, including pulsation, mass injection, and disk variability. So thank you very much, Jonathan. We're looking forward to your talk, and I'll turn it over to you.
Okay, great. Thank you, Carol. I am starting with sharing my screen, which I'll assume works unless anyone complains. It's not. Okay, sounds good. Right, so BE stars and their variability, mainly with space photometry. Right, so I'll just give a really quick overview of what a BE star is. I assume most of you already know this quite well. So these are main sequence B-type stars that form circumstellar decretion disks. It's kind of illustrated over here in the right in this picture. And these disks are built by mass that's mechanically ejected from the star, which is different from stellar winds. So a lot of hot stars eject mass through stellar winds. This is something else entirely. As a class, BE stars are near critical rotators. They are non-radial pulsators. They do not have large-scale magnetic fields, which is in contrast to about 10% of the non-BE OBA type stars. And BE stars are important for massive stars overall because they represent about 20% of B-type stars in the main sequence. So the disks of BE stars are their their hallmark observational feature. On the right, you can see kind of a movie of an H-alpha profile of a BE star disk. You have this double peaked emission feature because the disk rotates with a Keplerian velocity profile. And these disks vary over time in strength and in their radial density profile. They can appear and disappear. They also carry away mass and angular momentum from the system. So they cause stars to lose angular momentum in some fraction over their main sequence lifetime. But no one really knows how these stars manage to eject mass and angular momentum to form these disks. And I should say, once the disks are formed, they're governed mainly by viscosity. So that's kind of the mediating mechanism that causes disks to grow and evolve. I'll mostly talk about space photometry from the TESS survey. Of course, it's space photometry, so it's very high precision. Kind of the downside of TESS is that it only observes sectors for about 1 month at a time. So we're sort of limited to shorter timescales. But on the plus side, it covers basically the entire sky. I think something like 80% of the sky has already been observed by TESS in these huge sectors. So the field of view is enormous. It sees lots of stars at once, and you can extract very precise photometry from the TESS images. Here is just a picture actually from the TESS images of the entire southern ecliptic. So this is basically like 40% of the entire sky observed in the first year of the mission. And that's mainly the data set that I'll be focusing on now. So just photometry from the first year of the mission for about 500 BE stars. And I should point out that TESS is well suited for bright stars, even as bright as like naked eye objects. You can extract very nice photometry from TESS. So we're going to see a lot of light curves and frequency spectra. I guess my initial task of dealing with BE stars with TESS was just to figure out kind of what bins to put them in, how to organize the data to try to understand the variability of the population. So the first thing I did was grab light curves, extracted light curves from the images for about 500 of these southern BE stars observed in the first year, and then analyzed the light curves and the frequency spectra for various types of signals. You can have periodic signals, which manifest as sharp peaks in the frequency spectra. There's also stochastic variation, which is like a spectrum of peaks in the frequency spectra. And there's some other types of signals that we'll see in the light curves. So this plot just gives a quick snapshot of some of the diversity of variations we see in the brightness of BE stars. In addition to periodic signals, there's also some higher amplitude, slower changes in brightness that we see. You have periodic signals at different time scales, like the star here is kind of a slower pulsator, whereas these bottom few have higher frequency pulsation. And there's different patterns that arise in the frequency spectrum. So it's a good idea to try to understand what might be changing in these BE star systems that we see brightness variability. And generally, there's two broad categories. You can have changes that happen in the photosphere, either from pulsation or rotation. But with BE stars, you can also have circumstellar variability. Disks can build up or dissipate, they can evolve and change structure, and ejected material can sometimes obscure the photosphere, maybe causing a net dimming as the photosphere is blocked by ejected mass. So pulsation is going to be a really important part of BE star variations, especially with space photometry. And when a star pulsates, its temperature profile across its surface is kind of modulated by the pulsational mode. Generally, BE stars are non-radial pulsators, which are not spherically symmetric pulsation modes, and they're quantified by different quantum numbers. And as pulsation modifies the temperature across the stellar surface, we see wiggles in brightness, basically at the pulsation period. So there's a few different types of pulsation that might or do arise in BE stars. And the first one I want to mention are these internal gravity waves. So these might be a little different than what you usually think of as pulsation. These are driven by core convection, and this core convection excites a stochastic spectrum of frequency or of waves in the envelope, which is shown in this movie here. You can see convection plumes here in the convective core, and that excites these stochastic modes in the envelope, which changes the temperature profile across the surface. And we see this spectrum of low frequency variation, where the amplitude kind of drops off with increasing frequency. These are efficient at transporting angular momentum outward, which might be important in spinning up the envelope of BE stars. And importantly, they are basically observed in all OB stars. So you can look at these two papers and some more references if you're interested in that. And at the bottom is what these gravity waves look like in TESS. Then we also have kind of the more classic gravity mode pulsation, where gravity is the restoring force. These are well known in the SPB stars, where later type stars like B5, B6, and so on, the kappa mechanism acts to drive these gravity mode pulsations. But in the hottest BE stars like B0, B1, gravity modes are still observed, and they might be driven by these internal gravity waves instead of the Kappa mechanism. Usually these G-mode pulsations are observed at lower frequencies, and different azimuthal orders like m equals 1, 2, 3 affect the observed frequency that we actually see in a light curve. Kind of similar to gravity modes, we also have the pressure modes, or the P modes, which are higher frequency oscillations. These are kind of famous in the Beta Cephei type stars. And these are observed at higher frequencies, like 6, 8, 10 cycles per day or so. And then there are the Rossby modes, or R modes, which apparently were not actually seen in data until 2016. So these are a little bit newer in terms of what's actually been observed. And these are related to rapidly rotating stars, where the Coriolis force has some, actually serves to, as the restoring force for these modes. And they can couple to other types of pulsational modes. They're always retrograde, and they inherently form groups, usually just below multiples of the rotation frequency of the star. So this is what R modes look like in Kepler data for some star with R modes. Then in addition to pulsational variability, BE stars can also eject mass and build up a disk over time. And this bottom panel shows what these mass ejections look like in TESS. We usually see a brightening for a few days, followed by kind of a return back to a baseline level. And this can repeat or not. These can have various timescales. And I'll refer to these really short mass ejection episodes that last only for a few days as flickers, just to give them a name. All right, so on top of all that, there's extra complications I won't focus on too much. But it's good to know that when a BE star is ejecting mass, often it's very inhomogeneous. It can be clumpy. So there can be periodic variations or cyclic variations at the orbital frequency close to the star. You can have different pulsational modes that couple, which create even more frequencies in the frequency spectrum. Generally, the amplitude of any signals in a frequency spectrum can appear or disappear or change over time. BE stars might have binary companions, which might also contribute to any observed variability. And maybe some more further complications that I won't mention any further. So one thing that's been made clear by space photometry, not just from TESS, but with Bright and CoRo, MOST, and Kepler, is that BE stars are pulsators as a rule. And usually their frequency spectrum looks something like this, where you have signals organized into groups of frequencies. Just for, again, giving things names, I'll call this first frequency group G1, and there's usually a second frequency group called G2. And about 85% of the stars observed by TESS have groups like this, so it's a very common feature. Just a few more examples to highlight some of the diversity of the groups, but also show some of the similarities. Sometimes they start at lower frequencies and then kind of form a harmonic series where each subsequent group is some multiple of a previous group. Sometimes they're wide, sometimes they're more narrow. And just really quick on these plots, I show the frequency spectrum in the main part of the plot. And then the reverse of that, upside down, is the same frequency spectrum, but multiplied by 2. And the point of that is to show that, like in this case, this second frequency group here is basically the mirror image of the first frequency group, just at twice the frequency. And then likewise, this third frequency group is at about twice the frequency of the second frequency group. And they kind of have similarities in their shape. So there seems to be some relationship between the groups in these stars. But sometimes they're not mirror images of each other. Like here we have a very narrow group where the second group is very wide. In the top right here, again, these groups are very narrow. And sometimes maybe there's just one group. So one thing you can do when you have these groups of frequencies is you can kind of determine their center of mass by taking each frequency that belongs to a group and then kind of finding the weighted average. So in this star, this first group is located at about 1.7 cycles per day. And then the second group is about 3.4 cycles per day, almost exactly twice the frequency of the first group. So that's something we did for all the BE stars observed in the Southern Hemisphere by TESS. And that's shown in this plot, where this main ridge is just the central location of the first frequency group, going from half a cycle per day out to 3 cycles per day. And then the second ridge is the location of the second frequency group. And this gray band here marks 2 times G1. So you can see that most of these second frequency groups are scattered right around twice the frequency of the first group. And we see pretty much the same pattern for early, mid, and late type BE stars. The main difference is that earlier BE stars don't quite extend to as high frequencies as later types do, but otherwise their behavior is pretty similar in the location of the groups and their relative location. This just shows the ratio of the location of G2 divided by G1. And basically for early, mid, and late type stars, the distribution peaks right at around 2. So there's some scatter, but overall, G2 is located at twice the frequency of G1. So I think it's important to look at the location of these frequency groups and their spacing, because this study using Cura data showed that the spacing between frequency groups, they studied about 18 or so BE stars with Cura, and found that the group spacing is correlated to the rotational frequency as determined with spectroscopy. So this seems to provide a nice way to measure the rotation frequency of a star independent of inclination angle, which is obviously useful for a lot of reasons. You can also look at the relative amplitude of the groups. So if you just many ways to do this, but you can add up the amplitude of each signal that belongs to a group and then compare it to another group in that star. So here on the left, the first group is stronger than the second group, but that's not always the case. Sometimes the second group is stronger, or sometimes they're about the same strength. But this, on the other hand, the relative amplitude, seems to have some dependence on spectral type. So for example, the late type stars, the first group is almost always stronger or equally as strong as the second group. See, it's only 7% of late type stars have the second group being stronger. But for early type stars, it's about even across the board. It's just as common for the second group to be stronger or as strong or weaker than the first group. And I'll mention these numbers for flickers later. So in addition to the location of the groups themselves, of course, there's many frequencies within a group, and those also have important meanings and kind of relationships among other parts of the frequency spectrum. So when you have, anytime you have 2 frequencies close together in a star, you will basically always see this beating pattern. This is just a consequence of having 2 closely spaced modes where the difference in frequency of those 2 modes corresponds to the beat envelope. But this is not nonlinear coupling. On the other hand, for this star, 25 Ori, we have 2 main frequency modes spaced by about 0.2 cycles per day. And that corresponds exactly to a peak in the frequency spectrum. So there's this low frequency peak at a period of 5 days, which you can clearly see by eye just in the light curve. There's this slower modulation in brightness at a period that exactly corresponds to the difference between these 2 frequencies. And if you look a little closer, you'll see similar patterns throughout the frequency spectrum of this and many similar stars. So these combination frequencies, these are important because it means that these 2 modes are physically coupled and can actually produce many of the other signals that we see in the frequency spectrum. So most or maybe all of the signals in G2 here can be constructed by linear combinations of just these two modes. And the same with these lower frequency signals. These can be caused by differences between frequencies in the envelope. This idea of combination frequencies of mode coupling is not unique to BE stars. So in this example of a gamma door, a G mode pulsator, it also has frequency groups in its spectrum, or in its frequency spectrum. It kind of has lots of signals, as you can see. But all of these signals in the top panel, these can be constructed by linear combinations of just 4 different signals in the main frequency group. So moving on from pulsation a little bit, I will mention these mass ejection episodes, or these flickers or outbursts in BE stars. Let's see. Okay, so it's working. So this is a model of a central BE star, and you can see its disk around it. This is from H-dust models. And on the right, you see a simulated light curve. And as the star ejects mass, builds up a disk, the system gets brighter. But then if mass ejection turns off, the disk dissipates and it gets fainter. And this can go on for long periods of time with variable mass loss rates. But we see the opposite for edge-on stars, where the buildup of a disk actually causes a net dimming in the system because the photosphere is blocked by the disk. So this is what a disk buildup looks like in a light curve. The star gets, or the whole system gets brighter as the disk is built up, but then if mass loss turns off, the disk dissipates and the whole system gets dimmer. There's a lot of diversity in the outburst behavior of BE stars in general. So all of these plots have about an 8-year baseline, and they show different levels of variability with different time scales and kind of different cycles. So it's difficult to try to understand the outburst behavior of BE stars as a whole because they're so diverse. And especially with TESS, when we only get 1 month of data at a time, some stars are observed in multiple sectors, so we'll have multiple months. But even that is relatively short compared to the outbursts of some BE stars. But even despite these short observational baselines, we still see flickers in about 17% of the BE stars observed by TESS. And another really important thing that space photometry has revealed, not just with TESS, but lots of other satellites, is that the entire frequency spectrum often changes before, during, and after outbursts. So this is, again, what a typical outburst looks like in TESS. We see a net brightening and then a net fading back to baseline as mass is ejected and then maybe falls back onto the star or dissipates. If you take this red curve, which is just the lower frequency variation, and subtract that, you can see how the amplitude of the higher frequency signals can change during outbursts compared to before the outbursts. And that's also shown in this wavelet plot here, where the x-axis is time. So it corresponds exactly to the x-axis for these light curves, and the y-axis is frequency. So we have, again, these 2 frequency groups, and both of them are relatively strong during these 2 flicker events. So there often seems to be some connection between the strength of these frequency groups and the mass ejection events themselves. Every star observed by TESS that has flickers like this also has frequency groups. And in 83% of the stars with flickers, we see this enhancement of group strength corresponding to the timing of these events. Just another quick few plots to show some of the different types of, not different types, but different morphology of flickers maybe. So like in this top right plot, these events seem to repeat on maybe a 20-day timescale or so. And you still see enhancement of these frequency groups at the time of these events. Just one last example showing that sometimes when you have the onset of a flicker, you have enhancement in both groups, so G1 and G2. But other times, even though this is kind of small amplitude, this would still count as a short mass ejection event. You only see enhancement in the first group, and then a couple days later, there's another short flicker, and you only see enhancement in the second group. So it kind of depends on the star, it depends on the flicker, but usually one or both of the frequency groups are stronger during these events. Yeah, okay, so back to this figure that looks at the top right, that looks at the relative strength of G1 and G2. I mentioned that for stars with flickers, often G2 is relatively strong compared to G1. And that's shown as an example in this bottom plot. The first frequency group at about 2 cycles per day is a normal strength, but G2 is clearly stronger and is more associated with the timing of these flickers compared to the lower frequency group. That seems important, but I really have no idea why this is. So far, you've heard that these photometric flickers correspond to mass ejection, but there's a few cases where we can prove this. Just really quick, am I breaking up at all? I'm getting some messages that I'm unstable in my internet connection.
You're breaking up a little bit for me.
Sorry, let me just move location really quick to plug into the router here. Meantime, I'll leave us on this slide. There's more information to get. Okay, I should be good now. Right, so back to this slide. So in the light curve, of course, is test data for this star. And each of these triangles corresponds to a spectrum that was taken. And on the right, if you look at the H alpha profile, you can see how the emission grows corresponding to this flicker event in photometry. And if you measure the equivalent width of H alpha, you can see that, like the photometry, the equivalent width grows and then also fades, but with the slightly different timings, because different regions of the disk are probed by photometry versus spectroscopy. Just a quick note is that some of the students in our group are modeling these sort of events. So models of disk buildup and dissipation on very short timescales are shown on the right. And from these, we expect to be able to extract information about how much mass and angular momentum is actually being lost from the system during this short, like 10-day time span. So that will be interesting, but we don't have any results yet to talk about. So that last few slides demonstrates it's important and very useful to have spectroscopic data over the TESS observing baseline. Because it provides complementary information compared to the photometry. So we already know that pulsation modifies the temperature field, and we see variations in brightness. Sorry, it's trash day. But in addition to brightness modulation, pulsation also modifies the velocity field on the surface of a star. So if you convolve the velocity field from pulsation with the rotational velocity of the star, you get these distorted velocity fields, which leads to distortions in the line profile. And from this, you can extract information about the pulsation modes acting in the photosphere. Give me 1 second. Sorry, I just need to keep track of time. So to look at this a little further, I'll talk about one example of a pretty typical BE star 25-4. We've already seen its light curve, so we're kind of familiar with the system. In this star, I also observed it with spectra pretty intensively over its TESS baseline, getting about 180 spectra over this 1 month. And first, we'll just look at the kind of the pulsational information in these spectra. So I mentioned that the pulsation mode leaves a certain imprint in the line profile that changes with time. And the shell spectra are nice because you get access to photospheric lines, but also circumstellar lines. So first, we'll just look at a photospheric line. So the main pulsation frequency is here at this arrow. And the first thing to notice maybe is that it's different from the main TESS frequencies in photometry. This is just what the line profile looks like over time, this dynamical spectrum at this 1.7 day period, or sorry, 1.7 cycles per day frequency. And these other main peaks are just aliases of this single strong peak. But where are the TESS frequencies? We know these are real because these have signal to noise of like 1,000 or something in the TESS photometry. But we don't see them if we just measure the wobble of the center of the line profile. So, so this is kind of a terrible plot for a presentation, but I'll show it anyway. So this is the same photospheric line. And on the right, you see the average line profile. And the top is the blue part of the line, and the bottom's the red part of the line. And then in the middle, this kind of shows a 2D frequency spectrum, where the x-axis is frequency, like usual. But then the y-axis is broken up into velocity bins. So this bin here that I'm highlighting, this is a 50 kilometer per second bin between -250 and -300 kilometers per second. So we can see periodic features that change across the line profile. And then we can compare this to the TESS frequency spectrum. We have these two main TESS signals that show up about 1.3 and 1.5 cycles per day. And if you look at where those occur in the line profile, those seem to only exist in kind of the high velocity blue part of the line profile, whereas they're not really present at all in the red half of the line profile. Just to show that's not a fluke, this is a different line from the same star, same spectra. And again, showing that the photometric frequencies seem to only show up in the blue half of the line. So next, I want to look at some of the circumstellar lines in this star. So before doing that, I just want to highlight that basically in the first 2/3 of the TESS light curve, we have relatively high amplitudes in photometry. You can see that just obviously by eye or in the wavelet plot here, whereas in the last third, the amplitudes are present but lower. So just focusing on the first 5 or 6 days of the spectra, when we have this first broad bump in photometry, these are the deviations from average in the helium 6678 line profile. And this line is useful because it is sensitive to circumstellar material that's very hot and very close to the star. And there's some changes that occur on night-to-night timescales, and even within a certain night, or within a single night, over just a few hours, you can see some significant changes in the line profile. Just moving on to the next week or so of observations, again, still in the high active photometry phase. We see lots of variations from night to night. And one thing you might notice is that most of these variations are also in the blue half of the line profile. But we do see changes in the red half of the line profile as well, just not quite as much. And then in the final 6 nights, once the photometric variability has calmed down a little bit, we don't see nearly as much variation in the helium 6678 line. So this seems to suggest that there is less or maybe no mass ejection going on in these last few days, because the line profile is just more or less unchanging at a high level. So just zooming in on just a 3-night span, we can see the data from 3 different nights, each night spanning about 4 or 5 hours. There are pretty dramatic variations just from 1 hour to the next. Sometimes across the whole line profile, sometimes more on the high velocity blue edge of the line. And on this one night, we got many spectra over 6 hours. And again, at first, most of the changes are in the blue half of the line profile. But then 6 hours after the first spectrum, the entire line profile is much deeper compared to average. So there's changes in the very close circumstellar environment happening over timescales of just a few hours, at least during the first 2/3 of this TESS light curve. So I didn't show all these points, but from 25 Ori and comparing spectra to TESS, we learned that a lot of variations happen in the blue half of the line, sometimes at velocities greater than v sin I. There's correlations between the strength of spectroscopic and photometric activity. Lots of indications that this activity is happening very close to the star with velocity or with material at very high velocities. And there's some differences between the spectroscopic frequencies and the photometric frequencies, but there's also some links between the two. So if that seemed like we are understanding these BE stars, maybe not. So this is another BE star that has a lot of similarities to 25 Ori, which is kind of an arbitrary choice, but this was also observed with spectra many times over its TESS baseline. We see similar behavior in the TESS light curve, and they have very similar frequency spectra. So the top's 25 Ori, on the bottom is this other star. They both have frequency groups, they have low frequency changes. But for this other star, V434R, there is no mass ejection and no disk at all during the TESS baseline. So TESS cannot possibly tell us everything we need to know about these systems. We need additional information to attempt to understand the mass ejection properties of these stars. That's not to say this star does not ever have a disk, because in 2016 and 2017, it did have a disk. TESS data were from 2019. And then later in 2020, it had a disk again. So just a quick look at a long baseline light curve from the ground over about 8 years. We do see many short flickers in this star. They're low amplitude, but still real in the data. And we also see an overall dissipation of the disk over the first 5 or 6 years or so. Spectrum from early in this light curve shows a relatively strong H-alpha line, meaning a strong disk. And then later in the light curve, the disk is much weaker. So it's been dissipating over this time, even though there's occasional outbursts that build up the disk. So I mentioned 85% of BE stars show frequency groups. That means 15% don't. So what is going on with stars without frequency groups? How do those sustain a disk or eject mass? So one category of stars without groups are these stars where stochastic variation is kind of the characteristic variability that we see. That I can ignore. So just one example of a star that shows only stochastic variation is this star HR 6819, which is quite interesting to read about. If you have the time, I would recommend it. But there's no frequency groups, it's just stochastic changes in brightness, yet it does maintain a strong disk over many years at least. So groups are not essential for ejecting mass or growing disks in BE stars. But on the flip side, you have other BE stars with basically the same sort of stochastic variation, where in 13 years of spectra, there has never been any sign of a disk. So there's many examples of situations like both of these, but I'll just show two so you can contrast them. Kind of another situation, you may have stochastic variation plus P modes. So you don't have the typical low frequency groups that are common, but you have high frequency P modes. And stars like this can also somehow sustain a disk. So TESS observations from 2019 show high frequency pulsation, and spectra from 2020 show a reasonably, I mean, this is definitely real emission. So there is a disk around the star. Like the low frequency groups, you can also have coupling of P modes in the stellar envelope that produce combination frequencies, both at higher frequencies and also at lower frequencies. Okay, so from this, I guess not just with TESS, but from the past couple decades of space photometry, we've learned that all BE stars pulsate, and that they necessarily eject mass to form a disk, otherwise the disk would simply dissipate. Usually these mass ejections are in events called outbursts or flickers, but sometimes they happen more continuously over years or decades, where mass loss seems to be kind of constant. There are cases with links between photometric frequencies and mass ejection, but there's also cases without those links, like the stochastic BE stars with disks. When a BE star is ejecting mass, it's often not azimuthally symmetric or smooth, but it can be very clumpy, where you see a highly inhomogeneous, very inner disk as it's being built up. But then eventually viscosity smooths that out and creates a more symmetric disk. So there's, of course, some questions that remain with BE star variability. It's not totally clear to me exactly what frequency groups represent in all cases. It seems to be some combination of G and or R modes, but that might be a star by star thing. I don't totally know. Many BE stars have one single primary spectroscopic frequency and many photometric frequencies. And what of those two are important for mass ejection? Then there's a big question about how to explain the diversity of BE star behavior. You can have BE stars that have essentially the same exact frequency spectrum seen by TESS or other space photometers, but they have totally different mass ejection behavior or history or building up of a disk. So is it possible there are multiple mass ejection mechanisms? So you have smooth versus discrete mass loss. You have different types of variability in early versus late BE stars. This could be related to the rotational velocity of the star. The closer a star is to critical velocity, the less help material needs being launched into orbit. So maybe if you're closer to critical, you can eject mass only with stochastic variation that might provide enough extra energy and angular momentum to launch into orbit. And especially worth noting is that even though TESS is super precise, it's really not enough to understand the overall behavior of BE stars. We also need spectroscopy, both before, during, and after TESS observations to understand when mass loss is happening and kind of the profile of mass as it's being injected and as it's being integrated into the disk. So I'll stop here. If there's any questions, I am more than happy to answer them or attempt to.
Okay, well, thank you, Jonathan. That was a really interesting talk. Maybe before we launch into the questions, in case we lose the people that have to go for something else at 10, I'll just make a couple announcements, and people can just either raise your hand, ask the question in the chat, and we'll monitor those. Yes, but thank you, Jonathan. That was a very interesting, and it was nice to hear a nice summary of the TESS data and what it means for BE stars. So thank you. Just so everyone knows, the plan is to have a talk every about the third week of each month. We'll put the links and the updates on that BE Star web page where you found the link to this particular talk. So please circle back. We're working to update our web page. In future, we're going to have maybe some graduate students hosting the events too, so that they can have some experience helping facilitate the talks. So that's all upcoming and in the works. We also need to have an election for the IAU Working Group and Active B Stars executive. So if any of you, you have to be a regular member in order to serve on the executive, but if there are people who are interested and willing to serve and would like to stand for election, please let me know. I would really appreciate it. Anyway, I'll turn it back over. I see that Alex has got a raised hand, so why don't you start with your question, Alex?
Well, thanks, Carol. Thanks, Jonathan. This was a truly excellent talk. I'd like I have a couple of questions, but I'll start with one first, which is the relation between frequency groups, flickers, and mass loss. So you mentioned in the conclusion of your recent paper that 100% of the stars that have flickers do present frequency groups, but the converse is not true, right? You have lots of stars that have frequency groups that doesn't have any flickers in the light curve. So is that correct? Right. Can you say that 100%, so I got it right, that 100% of the stars with flickers do have frequency groups, right?
Yeah, exactly.
On the other hand, from that I get a picture that there is a causal relation between the two. On the other hand, at the end of your talk, you mentioned 6819, which is, as you said, a very cool star. And 6819, it does have a very stable disk, but has no flicker in the light curve and has no frequency group.
Right.
So does this seems to be a little odd in the sense that what's going on, right? I'd like to hear your comment about this. So what may be going on, right? If you can assume that for the star to sustain such a large disk, you would see flickers in the light curve, or what could be going on in this star 6819? It might be a continuous mass loss, or it simply could be that during the time of observations there weren't any flickers. So what are your comments about this?
Yeah, it's hard to say exactly. There do seem to be stars that sustain disks, also with like over time variable amounts of mass in the disk that don't seem to show any photometric flickers. But you're right that there always could have been flickers before or after the TESS observing baseline, especially if you only have 1 month or so. But yeah, I guess I would say I'm not convinced you need flickers or discrete episodes of mass loss to sustain a disk. It seems like some BE stars feed their disks in more of a smooth or continuous fashion. But even that still could have variable rates over time. It's just not mass loss turning off and on. It's just more of a time variable rate of mass ejection. But I have no plots or evidence to really support that at the moment.
I'd like just 2 comments on that before we go to someone else. The first one is that flickers may be invisible. Yeah. Right, observationally, in the sense that there are many situations where we can perfectly, I'd say a large flicker could be completely invisible in the light curve for many reasons. And another comment is that we'll say, okay, you said that one way to explain this apparent contradiction would be to say that you have a continuous mass loss, which would be a continuous flicker. A flicker is a mass loss.
Sure.
In which case, you do have mass loss without frequency groups, if that were true. Which would contradict a little bit the statement at the beginning of the talk. So I'm just pointing this up just to show how much we don't understand about these objects, right?
Yeah, it's definitely true that frequency groups are not necessary for mass ejection, even though they're so important in 85% or so of the BE stars.
Thank you.
Jonathan, I don't know if you can see the chat, but there is a question in the chat. I can read it if that would work better.
Yeah, if you don't mind, that would give me time to read it also.
Okay, it's from, I'm probably not pronouncing the name correctly, Anusha. So it says, ejection of material into the disk is clear, but in order to conserve angular momentum during this filling, there should be changes in rotational velocity, right? And then their question mark, how does that reflect on the nature of the light curves?
That's a pretty good question. Let me stall a little bit while I think about an answer to that. So there was this recent paper by Coralie Niener and some collaborators where they modeled the like internal gravity wave properties of I think like a B1 star. And they found that these internal gravity waves could transport angular momentum to the envelope and actually spin it up to increase the rotational velocity of the envelope, bringing it closer to critical. And at some tipping point, the envelope is close enough to critical that the simultaneous presence of pulsation modes then finally can overcome the, I guess, the last couple of kilometers per second to launch material into orbit. Whereas before the envelope is rotating close enough to critical, these pulsations are insufficient to eject mass. So it's possible that that idea is correct, is that there is some combination of actually changing rotation rate in the envelope plus pulsation that then act together to drive mass loss. But how that affects the nature of the light curves, I don't really know. I think the spin up of the envelope happens over, or at least is predicted to happen over timescales much longer than the TESS observing baseline. I think in this paper, I'm not sure where it is, but in that paper by Coralie, they found that like a 5 to 11 year timescale is typical or is expected for the kind of modulation of the rotation rate of the envelope. So I don't expect that to show up in light curves, but maybe with very careful spectra, that could be brought out of the data.
Very nice. Now I thought I saw another raised hand.
Carol, there's another question in the chat above that one, actually, that was asked before.
Oh, okay, go ahead and read it, Mark.
It's from Gaurav Banerjee. He says, one quick query, do you plan to carry out any follow-up work through photometry or even through spectroscopy to better understand the frequency groups in BE stars?
Yeah, short answer is yes. The slightly longer answer is that the TESS mission is still ongoing. So right now it's finishing up observing the Southern Hemisphere again for a second time. So that means that for all of these BE stars observed in year 1 of the mission, we'll have a second light curve. So one of the papers I'm working on right now with some of the grad students in my group is to kind of compare, so for each star to compare the frequency groups between year 1 of TESS and year 3 of TESS and see how they're changing. And if there's any corresponding changes in the disk or any other differences between those two windows that TESS observes the star. And also, since TESS is ongoing, in about 1 or 2 months, maybe, it's switching to observe the Northern Hemisphere. So I'm trying to get as much spectroscopic resources as possible to monitor the most interesting stars simultaneous with TESS, so that we can look at the variations in the photosphere, both with TESS, but also with spectroscopy. And I'm hoping that having many examples similar to 25 Ori, I just mean similar in the sense that they're intensively monitored with TESS and spectra, we might be able to get a better idea of what the TESS variations actually physically mean in the stars with the help of spectroscopy.
Thanks, Jonathan. Maziar, you had a question you put in the chat. Would you like to read it?
Yep. So thanks, Jonathan, for your presentation. And my question is, so it seems the late type B stars have longer and more stable disk formation and dissipation phases than the early type B stars. Do you see such a trend or any correlation in the frequency profiles?
I surprisingly, in general, no. Frequencies overall seem really similar between the early, mid, and late spectral types. The main obvious difference in TESS is the amplitudes, though. The early type B stars have generally have much higher amplitude of pulsation, maybe 10 or 20 parts per thousand, even up to 10% variations in brightness, where the later type BE stars seem to have the same sort of qualitative frequency groups and similar like widths, but the amplitude of the frequencies in late type BE stars is maybe 10 to 100 times smaller than that of the early types. So I guess in summary, the frequency profiles are the same, but the amplitudes are much, much lower. And I do agree that in, these late type stars, they seem to show a stable disk forever. There seems to be often no changes in the disk over many years, which is kind of in contrast to the early stars that have frequency groups plus flickers. Late type stars have frequency groups, but a stable disk.
Thank you.
Thanks, Jonathan. We probably have another, it's almost 10, but if anybody has we probably have time for another question or two.
There's one more person with their hand up, Carol.
Yeah, I had raised my hand. This is Anuprini.
I didn't.
And thanks, no worries. Jonathan, it was a very nice talk. Thank you. I had a couple of questions. One is, you mentioned at some time that the convective core may have something to do with the pulsations. So is there any way we can find out the amplitude of pulsation as a function of age of the star? Does it change? Like in the BE star itself, the question of whether the B becomes a BE at some time, then so is there any role for the pulsation to play as the star ages?
Yeah, I think so. So I think at least I understand, I see two parts to that question. So with the stochastic variation that is predicted to be driven by core convection. So I should also say a quick caveat. It's possible this sort of variation might be caused by a subsurface convection, but I just didn't talk about that much because I don't understand it as well. But if this stochastic variation is driven by core convection, then these papers by Bowman et al. And collaborators do show that older stars or more evolved stars have much higher amplitude stochastic variation compared to stars in the first half of their main sequence lifetime. So stochastic variation, yes, does depend on age. It gets higher amplitude as the star gets older. And also with the frequency groups, this paper by Seaman et al. Using Kuro data, not in this figure, but also in the paper, they show that the amplitude and location of the frequency groups also depends on age, where if I remember correctly, for more evolved stars, the groups shift to lower and lower frequencies. But I forget exactly what the relationships to age are. But yes, there almost definitely are relationships between frequency and evolutionary status and amplitude.
Yeah, thank you. So there's one more question I would like to ask is, how about BE stars with which are in binary system? Some have low luminosity companions, right? So do they behave differently?
I don't totally know it yet. I've started looking into the TESS light curves of known like BE plus SDO binaries. And overall, they show similar variations compared to, I guess, BE stars that are not maybe yet known to have binary companions. Yeah, I'd say that's still an open question. But there's no very obvious differences between those two populations of known BE binaries that really stand out in the data. But there might be subtle differences.
Thanks so much.
Thanks.
Okay, Mark, did I miss any other hands up?
No, I don't see any hands up, and I don't see any more questions in the chat. I don't believe so.
Okay. Oh, well, there is actually
one just
more.
popped up.
Yeah, one. Go ahead and read it, Mark.
Okay. Thank you for your fantastic presentation, Jonathan. I have a small question. If the signal to noise ratio is high, the frequency domain will reveal excited modes. How are these modes dealt with?
Frankly, I have no idea. I'm sorry, I can't answer this one. Yeah, if you have any references for where I might learn more about this, I'd be happy to try to follow this up, but right now I have no idea.
Okay, well,
brings me just a final one. Sorry, Carol.
Go ahead, Alex.
Could you? It's related to this last question. Could you comment a little bit about the prevalence, the fact that you detect more signals in the blue in 25 Ori, and the fact that in the spectrum of the star, in the blue, that's only in the blue you can find the photometric counterpart, right? Frequency, the same photometric frequency.
Right.
Do you have any idea as to what is going on, and why don't we see the spectroscopic frequency in TESS, which I find very confusing too?
Yes, I also find those two questions quite confusing. So I will say with with the TESS frequencies, these are, I'm 99% sure these are pulsation frequencies in the photosphere, because we very clearly see these two giving rise to combination frequencies. And these two frequencies cannot possibly couple if one of them is circumstellar and the other is photospheric. And it doesn't really make sense for circumstellar frequencies to couple in a coherent way. But as to why they only show up basically in the blue half of the line profile, I find very odd, and I really don't know what to make of that. I would say I only got to this point and made these plots at 2 in the morning last night, so it's not something I've really thought about so much yet. But this seems like a pretty important clue as to try to understand what these frequencies represent. Wait, what was the next one? Sorry, you had two there, and I forgot.
You don't see the same spectroscopic frequency. That could be understandable, I think, based on the geometry on the surface, perhaps.
Yeah, so it could either be like a geometric cancellation situation, where just if you have a certain sort of symmetry, you don't see a pulsational signature in the light curve. But you actually do see it very weakly. So, and you can still see my screen, I think.
Yes,
Yeah.
we can see it.
Okay. So this little dotted line here, this is the main spectroscopic frequency. And it is significant in TESS, but you might not notice it compared to the other signals if you didn't know where to look. And it's probably not a coincidence that it is equally spaced. Basically, it has the same like delta frequencies that some of the other modes do. But I agree, it's odd that it hardly shows up in the frequency spectrum of 25 Ori at all. Just on that same topic, there's another star that is similar to 25 Ori that basically observed the same way with spectra, and it shows the same situation, but even worse. So in this star, you have a really strong spectroscopic signal at this blue line here, and this is the TESS frequency group, and there's absolutely no power in TESS at the main spectroscopic signal, and essentially no spectroscopic power at the main TESS frequencies. So what is going on? I'm at a loss for exactly what that means. These might be two different types of pulsation modes. Maybe this spectroscopic signal is a G mode pulsation that somehow doesn't show up in photometry. And maybe these are somehow different. I really don't know though.
Well, thank you.
The message is that you need to look both spectroscopically and photometrically, because it looks like
absolutely
things, each technique reveals different aspects of pulsation, right?
Yeah.
Well, thank you. Thank you, Jonathan, and everybody for your comments. Jonathan, you gave a very, very interesting, excellent talk, and you stimulated lots of great questions and discussion. So thank you again for providing this talk to the group. And I'll be looking forward to the next talk in about 3 weeks' time. So thank you everybody for attending and for your participation. We really appreciate it. And thank you, Mark, for helping with all the Zoom issues. So, or not issues, but facilitating the questions. So thanks, everybody. And thank you, Jonathan. If we were all together, we'd give you a big round of applause.
Thanks. I really appreciate the opportunity. This was fun to put together.
Oh, great. Well, thank you. Thanks, everybody, and have a wonderful day. Bye.
Bye.